Hey guys, this is Gabin once again, and today we'll be looking at irrational and rational numbers. So rational and irrational numbers, right? So remember in the previous video we talked at the very beginning, we talked about rational numbers and irrational as well. However, today we're gonna do a review and maybe dig deep from where we left, right? So now we've got rational with irrational as a title. Now you can see this is the formal definition of rational number, right? Rational number, it's a number that could be expressed as a fraction, right? So a rational number is a number that could be expressed as a fraction, right? So we could have x equals a over b, where a and b are element of z or integers, and b has to be different from 0 because we cannot divide by 0, right? So that's the formal definition of rational number. However, on the other side, we have got irrational number. Irrational number, in the previous video also we talked about surd, right? So irrational numbers, pretty much that's one of the example of irrational number, which are surd, right? And then the idea of surd is basically saying x could be equal to any root of n root of a, right? Where n is element of n, which is natural number, and a has to be element of q, or rational numbers. So we could look further on examples, and the example that we've got here, we've got 4 on 15 and 19 on 12 and so on, and there are many fractions that we could write, right? So and the other thing here is on this side we have got square root of 2. This is a cubic root of 4, right? And so on. So you could have as many as cubic could change to 4th root or 5th root as n change, increases or decreases, right? Now we might wonder, okay, so yeah, that's the definition, the formal definition, and these are examples, but let's do a little bit of proof. This proof here is straightforward, but we're gonna do a little trick here. However, with this one we have to use one of the method, which is, I can't say hard, but then if you learn the technique, yeah, it becomes easier. So we're gonna prove this by contradiction, right? Proof by contradiction. Now let's start here. On this side here we've got, I'm gonna just prove 4 on 16, right? If you put in your calculator 4 on 16, it should give you a number, a decimal number. 4 on 15 should give you a decimal number with 6 recurring, right? So what you then have is, you have 4 on 15 is equal to 0.26 recurring. Now, so this is what you get if you put in a calculator. This is what you get. But then what I'm gonna do is I'm gonna prove using this, right? I'm gonna prove why this is why this number, if you get a fraction like this, why this number is a rational number, right? So remember in the previous video, that's what we've been doing. However, I'm gonna quickly go through this. So what do? What you do first, you have to find numerator. So numerator, right? The way you find numerator is you take these two numbers, which is 26 minus the number that is not recurring, which is 2, and then your numerator have to be 24. Now after finding the numerator, we also need to find the denominator. So the way you find the denominator is basically you take these two numbers. How many recurring number do we have? We've got one recurring number, so we take one recurring number. However, here I've got two numbers after the decimal point, so this will be 100, right? It will be 100, and 100 you take away, you times by 2, you take away 10, which will give you 90, right? And from 90, then 90 becomes your denominator because it's only one number that is recurring, right? So denominator will just be 90. And if you're not sure how about 90, watch the previous videos. We did a lot of two different examples on how you can convert decimal number into a rational number. So our denominator is 90, and what you then have, you have 24 on 90, and the 24 on 90, you can simplify this by 6. By 6 you get 4, and then here you get 15, right? And so you end up with this value, right? So this is a straightforward proof, right? Straightforward proof. Now I'm gonna prove this. I'm gonna prove the irrational part. The irrational part is a little bit tricky, but I'm gonna see how it goes, right? So yeah, let's get started. I'm gonna prove y square root of 2 is an irrational number. Irrational, right? So this is what we are trying to prove, right? So let's get started. This is the proof of y square root of 2 is irrational, right? Y square root of 2 is irrational. So what we did is, suppose square root of 2 is a rational number. Remember, I said that I'm gonna prove this by contradiction, contradiction. So we are proving this by contradiction. Now, what we do by contradiction, we suppose that the opposite of what we are trying to prove is true, right? So if square root is irrational, if we are proving that square root of 2 is irrational, then root 2 is, we suppose that root 2 is a rational number. Then what does that mean? We saw the proper definition of a rational number. So what it basically means is saying that we can find a and b such that they are integers, or integers a and b, where a and b only have a common factor of 1, right? A common factor of 1, such that we can write square root of 2 equals a on b, right? So this is the formal definition of a rational number. And when we do that, b has to be greater than 0, because if b is less than 0, it can have a square root of a negative number. And also that means if b is equal to 0, you cannot divide by 0. That's why b has to be strictly greater than 0. And what we did here, the next bit here, so remember these have to be integers, and they have to be common factor, only common factor of 1, only common factor of 1. And it's a formal definition. So here, when we are trying to get rid of the square root, what we do, we square both sides. When we square both sides, you have 2 squared. The square root of 2 squared is just 2, and on the right hand side we have 2a squared over b squared. And if you're trying to solve for a, you then have 2b squared equals a squared. Now, what does this mean? This means a must be even. Why? Because a squared is equal to 2 times b squared, right? This factor of 2, it's what tells us that a squared must be even, right? Must be even, right? And yeah, the definition, since the left hand side is even. Now, what does that mean? This means a squared can be even if a is even, right? So if a is even, then that we can guarantee that a squared is even, right? For instance, think about this. 9 is not even a number, even though 3 squared is 9, right? So just because it's squared, it doesn't mean it's even number, right? So, and with that, the same idea here, that's what we are using here. However, if a squared is even, that means a itself has to be even. And that's why we set a equals to 2k, where k is set a equals 2k, where k is another integer. Right? What does that mean? We can substitute expression 2 into 1, and when you do that, you have 2b squared equals 2k squared, and when you square both, so you get 2b squared equals 4k squared, right? So I hope that is clear. And then what we can then do is b itself equals to 2k squared, right? Because we divide by 2 on both sides, you get b squared equals 2k and b. What does this mean? This means b must be even number, and if b is even number, and the reason why b is even number because it's equal to 2k, right? This factor of 2 here, it tells us that it's b squared is even number, and b can only be even number if b itself is even number. What can we conclude from this? What we can deduce or conclude is both a and b are even. Both a and b are even. So if both a and b are even, what we then have is we have a common factor. What that means, it means that a and b, they must have a common factor of 2 because they are even. A common factor of 2 because they are even. This is a contradiction. This contradicts what we originally our original hypothesis, because what our hypothesis were suppose that a and b are rational, right? And they only have a common factor of 1, but then here we are proving that they have a common factor of 2, which is a contradiction to our original hypothesis, and therefore the hypothesis that we supposed or we assumed must be false. So if the hypothesis that we assume must be false, this is the end of the proof. We can surely conclude that root 2 is not able to be expressed as in the form of a over b, and if it cannot be written as a over b, then it's an irrational number. And this is the signature to show that we have finished our proof. Thank you so much, guys. I really appreciate your support.